So we are live streaming.
I forgot how to unshare my screen.
Okay, so hello everyone to the Post Quantum Cryptography session. So I remind you that we are bound by the ISER Code of Conduct, which means that you should use your professional name on Zoom in these online times. So it's my pleasure to introduce the moderators of this session, Serge Vodeny and Frédéric Verkouteren. And yeah, please take over.
Thank you very much. So welcome to this session. So in this session, we'll start with two talks, which will be on a Seaside, where we will have some sea fish. The first one is lossy sea fish efficient signature scheme with tight reduction to decisional Seaside 512 by Ali El Kafarani, Suishi Katsumata, and Federico Pintore. And Federico is giving a talk. Federico.
Yep. So thanks for the introduction. So let me start the presentation. Okay. So lossy sea fish is a new efficient isogeny-based signature scheme, which is a variant of sea fish and is tightly secure under the hardness assumption of a decisional problem over Seaside 512, is secure both in the classical and quantum random oracle model, and is almost as efficient as sea fish. In particular, the signature size is exactly the same. Public keys are twice as large as those of sea fish, and signing and verifying are at most twice as low. These results are obtained thanks to the introduction of a new lossy identification protocol. What was the need for a new signature scheme? Well, sea fish is the first practical isogeny-based signature specific to Seaside 512 parameters. Hence, it can offer at most the same security provided by a hard mathematical problem, GAIP, over the Seaside 512 parameters. However, sea fish, like every Fiat-Shamir signature, has a very loose reduction both in the classical and quantum random oracle model. To be more precise, the GAIP problem is believed to have 128 bits of classical security and at most 64 bits of quantum security. Therefore, assuming a modest 2 to 40 queries to the random oracle, no more than 44 bits of provable classical security can be argued for sea fish. However, a theorem by Kiltz, Lubashevsky, and Schaffner states that a Fiat-Shamir digital signature from a loss identification protocol enjoys a tight reduction to the hard problem on which the indistinguishability of lossy statements is based. That's the reason why we introduced a new lossy identification protocol. A lossy identification protocol is a modified identification protocol. So let X be the space of public keys and W the space of private keys, and R a binary relation that is a subset of the Cartesian product of X and W. A standard identification protocol ID for R is an interactive protocol composed by 4 probabilistic polynomial time algorithms. One of them, IGen, generates pairs of public secret keys. A lossy identification protocol has an extra algorithm, lossy IGen, which produces lossy public keys. That is, public keys for which not necessarily exist the corresponding private keys. We require these lossy public keys to be indistinguishable from valid ones. This is the indistinguishability of lossy statements that we mentioned in the previous slide. Now, sea fish is specific to one set of Seaside parameters, namely Seaside 512. For these parameters, we have an action star of the group Zn over a set X of elliptic curves. This action is free and transitive, so given two curves x0 and x1, there exists a unique A in Zn, sending x0 in x1. Inverting the action is a problem supposed to be hard also for quantum adversaries, and this problem is named GAIP, Group Action Inverse Problem. The binary relation used in CFISH, RCFISH, is composed by pairs XA, where X is an elliptic curve and A is an element of Zn, sending X0, a fixed elliptic curve, part of the public parameters, into X. So X is the public key, while A is the secret key. In this case, lossy public keys cannot be constructed, since each public key admits a unique secret key for the property of the group action star. In order to have lossy keys, we propose the following modified binary relation R lossy CFISH. So instead of considering one starting curve x0 as part of the public parameters, we split it into two random starting curves, xa and xb, which are now part of the public key. Then the same element A of Zn is used to compute two other curves, x1 and x2. These four curves form the public key. A is the secret key. Now, lossy keys can be constructed, and they are indistinguishable from valid keys, assuming the hardness of the Seaside analogies of the decisional Diffie-Hellman problem. Applying the Fiat-Charmy transform to the lossy identification protocol we introduced, we deduce the digital signature lossy CFISH. If we look at the parameters in the first line of the table, we can note that the scheme loses only one bit of the security of the underlying hard mathematical problem, supposed to offer the same bits of security of GAIP. The computational costs are dominated by the computation of group actions. So for the key generation, we need 2 times S plus 2 of M, while for signing and verifying, we need 2 times S of M. So making a comparison with those required by CFISH, we can deduce that our scheme is at most twice as low as CFISH. And that's all from me. Thank you. Thanks a lot.
Thank you very much. So there is one question already by Sakib.
Hi, yeah. So I was wondering if you tried to use this lossy relation directly, similar to the full domain hash results in the RSA variant, if that doesn't work immediately, or if you haven't thought about that yet. Thanks.
Thanks for a question. To be honest, I haven't thought about that. So I will have a look at this idea.
Okay, thank you.
Thanks. Yeah.
Okay, I think there is a question on a chat group. Markulf?
Yes, so I guess it's a kind of a speculative question, but do you think that the difference in tightness can lead to actual attacks on CFISH for the same parameters, and your scheme would still be secure?
Well, that's a difficult question to answer because I'm not aware of any practical attack for the moment, and I would say that it's also rather common to fix the security as done in CFISH. But it's also true that at the beginning of this year, there was a paper not about isogenies, but exploiting the non-tightness of the security proof for another post-quantum scheme. So this gives just the idea that it might be possible. For the moment, we don't have anything for CFISH or other isogeny-based schemes.
Okay, thank you. So if you have more questions, so you can put it on a chat group, and we'll come back to this later. So thank you very much for the presentation, and we can move to the next one. So the next one is threshold schemes from isogeny assumptions by Luca De Feo and Michael Meyer. So Michael will give the talk. And if someone wants to look at the FEO cursing, I strongly encourage you to watch at the pre-recorded video later. Michael?
Yeah, thanks for the introduction. Yeah, this is about threshold schemes for Mycenae assumptions and joint work with Luca De Feo. And first, a quick motivation for our work. In the last years, there have been some new isogeny-based schemes based on group actions, namely Seaside, which is a key exchange, and cfish, which is a signature scheme. And both of them are using the hard homogeneous basis framework for cryptographic group actions, which was defined by Couvenier. And actually, these hard homogeneous bases are an abstraction of the concept of discrete logarithm groups. So given that not much work has been done on threshold schemes for that are quantum resistant, the question we had in mind was, are the threshold protocols for discrete log groups still working in the hard homogeneous basis setting? So first we're going to look at hard homogeneous basis. We need a set E, which is equipped with a group action by a group G, and the cardinality of both has to be equal. So basically we're given a map that takes as input an element of G and an element of E, and outputs a different element of the set E. Now, of course, this has to be equipped with some hard problems, namely vectorization, which is the GEIP problem that Federico also already talked about, and parallelization. And actually, these two are analogous to the discrete log problem and the computational Diffie-Hellman problem. So if we look at an example, namely, we take the integers modulo p, acting on a discrete log group G, through the action s star G, which is G to the S, then this basically is a discrete log group in the notation of hard homogeneous basis. And then we can do linear secret sharing with this due to Desmet and Frankel. Namely, we can have a secret S, which is distributed in shares Si, such that the sum over all these Si equals S. So then these Si are distributed to the different parties. And when we want to recompute G to the S, then each party simply reveals Si star G, which is G to the Si. And then the combiner simply computes the product over all these partial answers to obtain G to the S due to the homomorphic property. Now, if we try to copy that protocol for hard homogeneous basis, we're given a starting element E0 of our set E. We're given a group element G, which is secret and which is shared into shares Gi. And we want to compute S star E0. And then there's a problem when we want to copy that protocol, because in general, we don't have a homomorphic operation on the set E, of course, because here it's a set and not a group. So the combiner cannot compute this product like in the last protocol. But there's a solution for this, which is quite simple. We have to adapt the sequential protocols, or have to get our ducks in a row, which means that the first duck starts by computing G1 star E0, passes on E1, then the second party computes its action, and so on. And finally, the last party gets the required element, G star E0. Now, of course, the more exciting protocol would be a threshold scheme. For example, we can use K out of N Shamir secret sharing, which relies on polynomial interpolation. And in this case, K out of the N parties should suffice to compute this secret action. But the problem here is that we need a ring for Lagrange polynomial interpolation to work, and therefore also for Shamir secret sharing to work. So thinking back to this Desmet-Frankel scheme for discrete log groups, we had the ring of integers modulo P acting on a discrete log group G. So we actually have a ring, and so this just works. We can just plug in Shamir secret sharing here, and this works perfectly fine. But in the case of hard homogeneous spaces, where the one-way function is this group action, we don't have a ring. We only have the group G and the bijection to the set E. So this does not work, unfortunately. So for hard homogeneous spaces and isogenies, that means that we would need an embedding from the ring of integers modulo P into the group T. But unfortunately, Seaside does not deliver such an embedding. So this does not work with Seaside. And also there was an obstacle for defining efficient signatures, but this was solved in Cfish. So Cfish gives us this embedding, and finally we can use this ring of integers modulo P acting on the embedding into the group T. We can use this to define the Charmier secret sharing and compute the action to the set E afterwards. So given the tools from Cfish, this actually works and we can define threshold schemes. So as a quick summary, we can define efficient threshold encryption schemes, key exchange, and signatures using Cfish and Charmier secret sharing. But there are some caveats. For example, we can prove them secure, but only in an honest but curious adversary model, which means that the adversary is still modeled to act honestly and follow the protocol rules. Then we have to adapt the round-robin communication structure and some more small caveats. And as a disclaimer, as Federico already said, Cfish is only defined for the Seaside parameter Seaside 512, and it's unlikely to scale to larger parameters. So that's a problem if we have to go to larger parameters due to the quantum security of Seaside and Cfish. And also some functionalities from the discrete log-based schemes don't carry over. For example, distributed key generation. So there's much more room for work to be done here. And finally, some advertisement here. Please go to YouTube and watch our video. Even if you don't care about isogenies or threshold schemes, I guess you'll enjoy watching this video. So that's all from my side. Thanks for listening.
Thank you very much. So is there any question? So maybe I have one while people are preparing their questions. I wonder, how long did it take to prepare your video?
That's a good question. That took quite long. Yeah, I mean, it took a few days to arrange all the stuff, and Luca wrote the script and find the costumes and do the setup, record the music. We did even that. Yes. Record the talk. So it took quite a lot of time, but I guess the result is quite funny, quite nice, and I hope people can enjoy. It's amazing.
Okay. Any question? Nobody raise hands. Nothing on the chat. Okay, so we can, thank you very much. So we can move to the next one. So, and I will let Frederic continue.
Okay, thank you, Serge. So the next talk is by André Chailloux and Thomas Derbry on tight and optimal reductions for signatures based on average trapdoor preimage samplable functions and applications to code-based signatures. And Thomas will give the talk.
So, thank you very much for the introduction. I share my screen. Is it working? Yes?
Yeah,
no?
We can see it.
Okay, perfect. So thank you for the introduction. So I'm going to quickly present to you our result with André Chailloux, who is here too, about tight and optimal security reduction for an extension of trapdoor preimage sampleable function, which are the functions that we call average trapdoor preimage sampleable function. So in the video that I present on internet, on YouTube, I quickly recall what is the aim of security reduction. So aim is to show that breaking a scheme, a cryptographic scheme, implies that breaking some problem that we believe to be hard. So I'm going to be very quick on these slides because yes. So, and in our work, we give a tight security reduction, which means that if we break a scheme in time t, then we can break some problem in time approximately t. So in our model, in our security reduction, we use a random or oracle model. And this kind of model are used when some schemes need a function that behave like a random function. For instance, if you use a hash function, and in the random oracle model, you model your hash function as a random function. And there is an extension of this model, which is the quantum random oracle model. And in this model, you have access to a quantum computer. So from a classical circuit, you can build a quantum unitary circuit, and with this quantum unitary circuit, you can make a superposition computation of your inputs, and the running time of your quantum circuit is approximately the same as the running time of your circuit. And in the quantum random oracle model, we suppose that an adversary has access to the hash function, so it can make superposition computation with the hash function. So this model are often used for signatures, especially in the case of full domain hash signatures. And I quickly recall what it is here. It is a signature scheme where you use a hash function, a trapdoor one-way function, and to make your signature, you just invert your function with your secret. So in this kind of scheme, you use a hash function to hash your message that you want to send. So we are going to suppose in the following that the hash function is completely random. To build such a signatures, to assert the security of such signatures, we have a classical model, which is a CMA model. And what is important to know in this model, sorry, I'm very quick, is the fact that an attacker can ask to the signer to sign any message of its choice, and the attacker has access to a hash function, which is modeled as a random function. So in this kind of model, if you want to have a tight security reduction, we have the result of Gentry, Peikert, and Vakunathan, who propose to add some properties to the trapdoor one-way function that you use in your signature scheme. Why? Because the attacker, any attacker has access to signature of his choice, so we don't want any leakage on the secret key that is used to invert the function. So they propose to add some property to the function, and they introduce the concept of pre-image sampleable function that I will call TPSF in the following. So to give a quick definition of this function, this kind of function. So you have your trapdoor one-way function that you know how to invert with your secret key, and you have a distribution D, which is public, and your function needs the two properties, which are the following. First, you need that the algorithm which inverts your function on any input has a distribution which is extremely close to the distribution D, conditioning on the event f of x here is equal to y. And there is a second property. It means that f of x, when x is picked according to D, is close to the uniform. In some sense, these two properties mimics what's happened in the case where the function f here is a permutation. So they applied the result to a lattice construction, and where they use a one-way function f, such that invert the function is exactly the problem ISIS. And with the pre-match sampleable property, they gave a tight security reduction to the collision problem for the ISIS problem, for lattice problem. And here we have a diagram which shows that as they made a security reduction to the collision problem, making a collision is easier than forging a signature, which is easier than inverting the function, the one-way property, which is ISIS. And for the GPV parameters for the construction, the difficulty of ISIS is quite the same as the difficulty of SIS. So they make a very tight security reduction in the sense that they show that forging a signature is exactly inverting the function f. So here there are two questions. They made the tight security reduction to the collision problem. Is it necessary? And secondly, they need the pre-match sampleable properties, which are very hard to meet. Can we relax them? In our work, we propose to relax the definition of TPSF to the notion of average TPSF. And we gave a tight security reduction to the claw with random function problem that I will present just after. And we made an extension of this result in the QROM. And we applied this tight security reduction to the new code-based signatures wave. In this case, it was crucial because for the wave parameters, the collision problem is easy, so we cannot make a reduction to it. So here I will quickly explain how work the average TPSF. So with the two first point here, we have the precise definition of the trapdoor pre-image sampleable properties that you need. The first property exactly means that when you invert your function here, you need the distribution of this to be very close to the distribution of D, knowing that f of here es is equal to your input. Here it is important to notice that this property needs to be true for all input. And the second property that I just gave before is that the image of your function are close to the uniform for the statistical distance. And in our case, we just relax these two properties into one. And here we ask for the algorithm which invert your function to be close to the distribution D, but when inputs of your algorithm which invert your function are uniform. It means that we relax the first point of the property into from we need for all input to in average over the inputs. And in this case, what is important to notice, it is when you have an ATPSF, then you have a TPSF, sorry, there is a typo, but there is a loss in the parameters. Why? Because when you have the here epsilon property of ATPSF, then you have a square of epsilon for the first property of TPSF. So we cannot use directly the result of GPV to make a tight security reduction because we have a loss. And that's why we made the security reduction. And now I just want to notice to you that we only know now, to the best of my knowledge, one TPSF, which is the Falcon scheme, and the ATPSF wave that I just spoke before. So I just would like to present to you the problem in which we reduce for security reduction. It is the claw problem, the claw with random function problem. So in your problem, as instance, you have a function f, which is your one-way function in some sense, and you have a random function h, to which we only have access as a black box. And your goal is to find a collision between these two functions. So we first showed in the paper that breaking this problem in time t with q queries to h implies that inverting f in time q times t. And in some sense, you can see this problem as trying to invert your function f, which is your one-way function, where you have many inputs on which you can invert it. It means that you can compute the function h on many inputs y. You have many h of y, and your goal is just to find a preimage for f for one of these y. So it is a problem in which we made our tight security reduction. So now I will skip the sketch of the security reduction and just to give to you a quick conclusion. So we made in our work a relaxation of the GPV condition to make signatures the full domain hash paradigm, but with the tight security reduction to the claw with RF problem. Maybe it opens new opportunities to make signatures because making an ATPSF is easier than making a TPSF. And in the case of codes where we applied our reduction, the claw with RF problem is a well-known problem, which is known as decoding one out of many problems. And in this case, for the wave parameters in the state of the art of algorithm, the algorithms which solve the doom problem have essentially the same complexity that the problem which solves the decoding problem, which is exactly the problem to invert your one-way function. So in some sense, for the wave parameters, we show that forging a signature is essentially the same as solving the decoding problem. So thank you.
Thank you for your talk. We have time for one quick question. So if somebody wants to ask a quick question, that's possible. If not, if there is time left at the end, well, you can also ask questions then. So I don't see anybody raising their hand. So let's go to the next talk. This is on generic authenticated key exchange in the quantum random oracle model by Katrien Hovelmans, Eike Kultz, Sven Schege, and Dominic Unruh. And Katrien will give the talk.
Yeah, thanks for the introduction and welcome to my short talk in which I'll try to sell our paper on post-quantum secure key exchange. So if you believe in quantum computers, constructing post-quantum secure key exchange is really crucial because it's such an important building block in our security systems. And hence it might be a bit of a surprise that NIST did not require submissions to specify a concrete AKE protocol. And my guess is that this was due to the assessment that AKE protocols can be constructed from lower level primitives quite in a straightforward manner. And what I want to do now is to challenge this assessment a bit due to the following reasons. So pre-quantum, the situation was quite easy. We were using Diffie-Hellman key exchange and authentication via signatures or key encapsulation mechanisms. Post-quantum, the situation is a bit more complicated because Diffie-Hellman key exchange is broken and the signature constructions we know of as of today are still quite costly. So we would like to do without them. And an obvious workaround would be to just use post-quantum secure key encapsulation mechanisms instead. But then the question arises, how exactly do we use them? What I want to discuss now is prior work that has given CAM to AKE constructions and why they might be unfit for our setting. So known constructions were given in the work by Boyd et al. In 2008 and by Fuyuka et al. In 2012 and 13. But the construction given by Boyd et al. Only achieves a sufficient level of security if they rely on Diffie-Hellman. And we already know in our setting that's not great. And the work by Fuyuka et al., so both papers, require the underlying scheme to be perfectly correct, which is a property that's not common for all lattice-based schemes. For example, take Kyber or Frodo or New Hope. They all have some small probability of decryption failure. By that, I mean that first encrypting, then decrypting does not yield the original message. And yeah, I already mentioned this is a small probability, so you might wonder, how is this even an issue? But what we've seen within the last years is that at least for post-quantum key encapsulation mechanisms, this negligible failure probability is not a negligible issue. And I'll talk a bit more about this in my full talk on YouTube. Another minor issue when it comes to the constructions by Fuyuka is that they are applied to a CAM that's usually already derived by applying the Fujisaki-Okamoto transformation. And both constructions involve quite a lot of hashing. And if you plug them together, the whole construction might be viewed as a bit overly complicated. But the more important point is this correctness requirement. So summing up, all of the constructions that were given before might turn out to be unfit if we want to achieve post-quantum security for schemes that come with a small probability of decryption failure. And hence, the goal of our work was to give a simplified transformation that is post-quantum secure, even when applied to schemes with non-perfect correctness. And how did we get there? So what we did was to give an AKE extension of one of the Fujisaki-Okamoto-like CAMs that have been around for a few years now. I'll give more details on how this extension works in the full talk. And as a helper result, we also give a security proof for the aforementioned CAM. And if you're wondering, are we still not done yet with those Fujisaki-Okamoto-like key encapsulation mechanisms? There will also be some details on this issue in the full talk. And a nice application is the Kyber AKE protocol, because its security statement basically consists of applying this work to the Kyber PKE scheme. Yeah, with that, I want to conclude my talk, and I'd be happy to answer any questions. And you could also write me an email or contact me via Twitter. Thanks.
Thank you for your talk. Again, same thing. If there's any question, please raise your hand. I have a question actually. So what is the extra cost involved in this versus the Kyber chem, the normal chem?
I'm not sure if I understood the question. Could you rephrase it?
Yes. So if you do the normal approach where you do Kyber plus FO, so what is the extra cost of your construction compared to Kyber with FO?
So the Kyber chem is constructed from applying FO, and we do not know of any constructions that can turn this kind of FO chem into an AKE scheme that is secure. So what we did instead is to work with the passively secure PKE scheme and apply our AKE construction. I hope this answers your question.
Yeah, but what is the cost involved? I mean, compared with FO, which is just a couple of hash functions.
I don't think it makes a lot of difference because we also only involve a lot of hash functions here, but maybe I have to think about it and we can take it offline.
Okay, thank you. Any other questions? Don't see anybody raising their hand. So then the final talk of the session is on threshold ring signatures, new definitions and post-quantum security by Abida Haq and Alessandro Scafuro, and Abida will give the talk.
Okay, so hi everyone. Today I'll talk about threshold ring signatures, and I'm going to focus on explaining what the threshold ring signatures are, and then how we were able to achieve post-quantum security. Since I only have 5 minutes, if you're interested in knowing more details, then you can email me or check out the paper on ePrint. So very quickly, a threshold ring signature is where T distinct parties anonymously sign on behalf of a ring of n public keys. So you see here, the example I made was with n is equal to 5. And so we have T is equal to 3.
Can you share your screen?
Oh, my screen is not being shared. I'm so sorry. Okay. I'm so sorry. Okay. So the a threshold ring signature scheme is where T distinct parties anonymously sign on behalf of a ring of n public keys. So the example that I have here is with n is equal to 5, and then you have 3 signers and then 2 non-signers. And what the signers can do is they can use their own secret keys to sign the message. And when the verifier receives the message, he's going to be convinced that it actually did come from, in this case, at least 3 different signers. So that's the concept of unforgeability in the scheme. But he's not going to know which particular 3 members it was out of the 5. And that's the concept of anonymity in the scheme. So in previous works, there's 2 reasons that a threshold ring signature scheme might be post-quantum insecure. Either because they use non-post-quantum secure problems like discrete log or factoring, but more importantly, all of these schemes are using fiat Shamir, and it's not necessarily true that the way that they've used fiat Shamir is post-quantum secure. And the reason for that is because normally fiat Shamir is proved with rewinding, but because now this middle step has been replaced by access to a quantum random oracle, the adversary can ask in superposition. And so it means that being rewound might actually be noticeable. So the solutions to this problem for now are, first, we're going to provide a black box construction from any post-quantum secure trapdoor commitment scheme. So that sidesteps the issue of the hardness problem. And then also, rather than using the fiat Shamir transformation, we will use the Unruh transformation. So quickly, a trapdoor commitment scheme with knowledge of a trapdoor, the sender can open a message, a commitment to any message they like. So it's a commitment scheme still, so we still have hiding and binding for honest commitments. And then additionally, we have trapdoor indistinguishability, so it's not possible to tell trapdoor or honest commitments. So now with the protocol, the signers know their own secret keys, of course, and they can use these secret keys are actually the trapdoors for a commitment scheme. Whereas for the non-signers, they only know any public information associated with the commitment scheme. And so this is what the signers are going to use. They're going to create trapdoor commitments for themselves and honest commitments for the non-signers. So you see here, we have all the signers have their commitments and all the non-signers have their commitments, which can then be gathered up into a vector. And this vector is what's going to be sent to the random oracle. And using secret sharing, it's now possible for the signers to decide how they want to open their commitments so that they're all consistent with the challenge Z. So now we have a lot of commitments and we have a lot of openings, and the verifier is going to receive those commitments and openings. Now, because all of these openings are consistent with the challenge Z, the verifier is going to be convinced that at least 3 out of 5 people participated, but he's not, since he can't tell the difference between trapdoor and honest commitments, the anonymity of the scheme holds. Unforgeability is going to be slightly more involved than anonymity, because the proof technique will require going into all honest commitments and then somehow using a forgery to break binding. And normally that would be done with rewinding to get 2 different sets of openings. But we can't do that here. So this is where the under transformation comes in. So the template stays, but now instead of receiving 1 challenge from the random oracle, the signers actually receive M challenges, and they have to provide openings for all of them. But what they're going to provide to the verifier is only going to be 1 vector of the openings. Finally, all the other openings are going to be hidden by this invertible hash. And later on in the proof of unforgeability, this hash can be inverted and you can find 2 different openings. And so this sidesteps the issue of having to rewind, because by providing all the answers right away, we have this concept of straight line extractability. So that's it. So just in conclusion, we provided the first post-quantum secure threshold ring signature scheme. And we also provided new security definitions. So if you're interested in learning more, the ePrint link is there, or you can of course email me, and I'm happy to take questions now.
Thank you. So we have a question from Serge, I see. So Serge, go ahead.
Okay.
Okay. So I was wondering, so there was a nice paper by recent part and ELEC at Eurocrypt 2006 about rogue key attacks against ring signatures, multi-signatures, where he explains that we need a proof of ownership of the public key. So I guess the same applies here.
So I'm not sure what proof of ownership is actually.
So if a malicious participant register a rogue key, a rogue public key, then presumably he can break the anonymity of the signatures.
Oh, okay. So I didn't talk about it in this talk, but the way that our security notions are set up for anonymity, we actually require that only honest, like for the challenge, when you're trying to distinguish between 2 sets, that we only have honest keys. And so the security model that we do already is avoiding this issue.
Okay.
So we have a raised hand from Simona. Is the question for Abida? If so, you can ask the question.
Yes, yes. Thank you for your presentation. Can you tell me, in light of the new proofs of Dawn and Mayans and Schaffner of the security of Fiat-Shamir in the QROM? So we know that they can be proven secure in the QROM. So what would be the difference, and will there be any, let's say, practical difference in just, doing it with Fiat-Shamir?
Sure. So one thing you might notice with the UNRU transformation, because you have to provide all the openings, that the signature is quite heavy. So if you're able to use Fiat Shamir in a provably post-quantum way, then you could provide probably a threshold ring signature scheme, which is much smaller. I do think that the results from Dawn, and also there was Ward Buelen's paper for how to apply Fiat Shamir. I think that these might be, it might be possible now to do, as long as you set up your assumptions correctly, that it will be possible to create this same template, but to use Fiat Shamir instead. So that would be an interesting question for future work, I think.
Okay, we have a couple more questions for Catherine. So Cyprien, do you want to ask your question?
Can you hear me all right?
Yep.
Well, actually, Catherine's answered it pretty much already. But I will ask for clarification. I don't remember what MEX stands for. That's my bad on not doing my homework. But if Catherine could just specify that.
You were asking what MAX means?
Yes.
Maximal exposure attacks, where you can corrupt the user and get access to the session's internal data.
So it's state reveal combined with long-term key reveal.
Yeah,
Right.
but of course you cannot allow both on one of the communicator side, because then you could trivially break any two-pass protocol.
Yeah, okay, thanks.
Mm-hmm.
Okay, we have another question for Catherine. Mark Ulf.
Yes, so I asked the reason why CPA secure public key encryption scheme is used and what the state of the art is. Like, seems surprising to me that we don't know how to build a CCA secure post-quantum scheme, or that we don't know how to build authenticated key exchange from that. But I guess this is an interesting question. Maybe you can summarize again the state of the art there.
Yeah, what I'd like to say here is that we weren't smart enough to come up with a passive chem to active chem transformation. This would have been better, but we didn't manage to.
But Fujioka Okamoto doesn't do that, or that would have been my guess.
No, so the recent Fujisaki Okamoto can start from a PKE scheme that is passively secure, because exactly of this reason, we do not know how to turn a passively secure chem into an actively secure chem.
Okay.
Any further questions? No? Okay, so then let's all thank the speakers. And yeah, this is the end of the session, I guess. Serge, do you want to say anything?
Thank you very much. Thank you to all the speakers and participants. And then we'll have a 20 minutes break now. See you at the next session.
Bye, everyone.
Bye.
Bye.